Okay, our next speaker is, I'll say it in Dutch, Frank van der Bos. The floor is yours.
Thank you. I'm going to talk about dynamical friction, core stalling, and dynamical buoyancy, which is a project I've worked on in collaboration with this young man here, Udipan Banik, who is a finishing graduate student at Yale. Now, I don't, at this audience, have explained why dynamical friction is important. It's the main agent that causes galaxies inside halos to merge. It's important for bringing supermassive black holes close enough together that gravitational wave radiation can take over and cause them to merge. And you've all learned in grad school about a derivation, how dynamical friction works. This was first worked out by Chandrasekhar in a famous 1943 paper. And a picture that is often shown is one where an object moves to an infinite homogeneous sea of particles. It then gravitationally deflects particles behind it, creates an overdensity called a wake, and it's the back reaction of that wake on the perturber that causes this object to slow down. Okay, and it's often, most of you have seen this expression for the dynamical friction force worked out by Chandrasekhar. And it turns out that this simple expression actually works remarkably well in explaining dynamical friction as we see it in numerical simulations when we do experiments of, say, a dwarf galaxy falling inside a bigger halo. But it doesn't always work. And a famous case where it fails was first demonstrated by Tobias Gert and Justin Reed in 2006. What it is, they ran a simulation of an object sinking in a big halo, but that halo had a large constant density core. And what they found is function of radius, time here, that initially the object did exactly what Chandrasekhar's formula told it should do. It was sinking in, but then at some point it came close to the core radius and it just didn't want to go in any further. It stalled. This has been reproduced in many simulations and it's known as core stalling. Now, even more amazingly, in 2012, Cole and collaborators asked the obvious question, what happens if I take a massive object and put it inside the core to start with? And what they found was that the object actually gets pushed out. It got pushed out over time until it again settled roughly at that core radius. And this has become known as dynamical buoyancy. Now, neither buoyancy nor core stalling can be explained by the simple Chandrasekhar prescription. That again shouldn't come as a surprise. Okay? Chandrasekhar is derived from an infinite homogeneous sea of particles, which is a poor description of what a halo looks like. Okay? And it was Tremaine-Weinberg in their famous 1984 paper who actually derived a better approximation or description of dynamical friction, okay, taking into account that you have a spherical halo through which you're moving. And what they found was that basically dynamical friction is entirely due to stars that are on resonance with the perturber. And if you think about that for the first time, at least when I heard that, I was like, oh, why only resonance stars cause dynamical friction? So my goal here is to try and explain how that works, and then show how you can use the same ideas to explain core stalling and buoyancy. All right, so what Tremaine and Weinberg did was they took the collisionless Boltzmann equation. So here it is, distribution function, Hamiltonian. These are the Poisson brackets, okay? And they perturb the Hamiltonian with the perturbation, which in this case is your perturber moving around in that halo. That perturber then causes a perturbation in a distribution function, which we call the response. Okay? And the goal is to calculate the response. How does the system respond to that perturbation? Okay, you just plug these expressions in this equation, you linearize it. Okay, this is just standard perturbation theory. You solve then for F1 mode by mode, because you do this in Fourier space. This is exactly what you do in perturbation theory that describes structure formation. Okay? And what you then want to calculate from that response is the torque. Okay? If you think about the response, you integrate over velocity, then you get the response density. And the way to visualize that response density is basically that's that wake that is created behind that perturber. And that wake now exerts a force on the perturber that's misaligned with the radial vector that gives rise to a torque. And that's the thing that slows down and causes dynamical friction. Okay? So you want to calculate that. In order to calculate the torque, you have to integrate over all of phase space of that response. Okay, typically what you do is you do a canonical transformation to action angle variables. You may have heard of that. And you have to sum over all the modes, and you get an expression for the total torque. Okay. Now, when you do perturbation theory, you always have to ask yourself, how am I going to introduce the perturbation? And the way this is standardly done is to say, well, let's assume that we just introduce it according to this exponential increase over time. up to time t is 0, which is the time at which I want to compute my torque. Okay, so you just multiply this by e to the gamma t, and at the end of the day, when you're doing your calculation, you take the limit, gamma to 0, which is called taking the adiabatic limit. You're basically assuming that the perturber, it took infinitely long for the perturber to slowly get to where it is today, so that the system can adjust to it, okay? And that's what you do. And if you do that, and that's what Tremaine and Weinberg did, you get finally this expression for the torque. Now, it's a complicated looking integral, but I'll walk you through it. Basically what it is, it's an integral over all the actions, and you sort of just think about this as an integral over all orbits, okay? Now, the next part is the most important part, because you see there's a Dirac delta function there, and a Dirac delta function mainly means you only get a contribution from orbits for which this is 1. In other words, for which the argument is 0. And Lk omega k is shorthand for L1 omega 1 plus L2 omega 2 minus L3 omega p. L's are just integers. Omega 1 and omega 2 are the frequencies of the stars in your halo. These are the eigenfrequencies of the stars. Omega p is the frequency of the perturber. So this is a commensurability condition. And basically this says only the orbits for which this is true, in other words, only the resonant orbits make a net contribution to the torque. Okay? This is the gradient in the distribution function, which plays an important role, as we will see later on. I'll try to explain to you why that is. And finally, you have the Fourier modes of the perturber potential, because obviously the torque depends on the perturber. Okay? Now, what you then do is you sum over all the modes, all the different L, basically, and you get this expression for the torque, which has become known as the LBK torque after Lynden, Bell, and Kalnash, who first derived it to describe how spiral arms torque stars in a disk. And the one thing I want you to notice is that, look, there is a gradient here in the distribution function, and that gradient is always negative, because if it was positive, a system with a positive dFdE is unstable. Okay? So you can't have a halo like that. So this is always negative, this is positive. In other words, the LBK torque is always negative. It's always retarding. It always causes friction. It can never cause buoyancy. Okay, so that's a problem. But the LBK torque can explain core stalling. And this was first shown in the paper 2018 by Kaur and Sridhar. This is radius as a function of time. Okay, you do a calculation of an object sinking in a halo with a constant density core. Chandrasekhar says, oh, it just continue to sink. But if you replace the Chandrasekhar formula with the LBK torque, what you get is this. It stalls, consistent with what we saw in the simulations. Okay? So that's good news, but as I said, there's no explanation for buoyancy. Now, we have to go back to that LBK torque and look at it again. And then we realize that this Dirac delta function is a direct consequence of taking this adiabatic limit. That's where mathematically this Dirac delta function pops in. And of course, it's not physical that it takes infinitely long for the perturber to get there. So let's change that and see what happens. So if we take the other crazy limit, gamma to infinity, that basically means we assume that we instantaneously introduce the perturber. Okay? Now that's also unphysical, but at least that's what the simulators do often. When they simulate the system, they set up an embody system, put the perturber in and let it go. Now what you get then for the torque is slightly different. Basically the only thing that changes in the math is that your Dirac delta function turns into a sine function. This has two important implications. First of all, it means that now all orbits contribute to the torque, not just the resonances. And secondly, there's a sign here as function of time. That means you get both positive and negative contributions here. That means you can now make your torque positive. You can now cause dynamical buoyancy. And if you actually look at this sign here, that means that each individual orbit sinusoidally changes the sign of the torque from being positive to negative. Okay, so this is weird. Let's see what this now does. Oops, sorry. Let's see what this does if you actually calculate this. So this is now the torque for a particular mode as function of time. The dashed lines are the LBK torques for those modes, computed with this expression here. Okay? And the solid lines are the corresponding modes according for the instantaneous introduction. And you see a very different picture. You basically see these huge oscillations. These are transients. And these transients slowly die out over time, and in the long time limit, you approach the LBK torque. Okay? So we have to understand what this transient behavior is doing. But the one thing I wanted to point out is that, look, it takes a long time to die out. This is 20 orbital periods of that perturber. Okay? So in reality, we should expect some of this transient behavior to be present. Now, why is there a transient behavior, and in particular, why does it die out? Well, it's simple to understand by simply taking an analogy of a bunch of harmonic oscillators. Okay? In a galaxy, each star basically has its own frequencies. Okay, so if I have a bunch of oscillators with different frequencies, and I perturb them, and I now let them go, what's going to happen is I get a very coherent response. They all go in the same direction. Okay? But over time, they have their own eigenfrequencies. They get out of phase, and I lose the coherence of my response. After a little bit, I have, on average, as many pendulums on the left as on the right, and basically I have my perturbation has died out. Okay? Now, in the case of the galaxy, okay, what I have is I have a bunch of stars that are going around with their own eigenfrequencies. I'm perturbing the system. I'm forcing these oscillators now around with a particular frequency. This response will die out because of phase mixing of all these stars. They all have different frequencies. That's this dying out of this transient behavior. The only orbits that cannot get out of phase with the perturber are the orbits that are on resonance. So in the long-time limit, the only one that survives are your resonance orbits. Okay? All right. Now, let's look again at this equation, because there's another problem with it. Not only is this Dirac delta function basically not well motivated, because it assumes an infinite time to build up my perturber, you also see that here there's no time dependence in my perturbation. In reality, the torque here will cause the perturber to sink in, right? Dynamical friction. And that means you want to take into account that this thing is time dependent. And by not taking that into account, you're basically making something known as a secular approximation. You're basically assuming that it takes very long for this thing to sink in. But if it takes very long, it's not very interesting. Right? So what you really need to do is you need to take into account the fact that this thing is sinking in. But in order to calculate how fast it's sinking in, I need to be able to compute the torque. But in order to compute the torque, I need to know how fast the damn thing is sinking in. And this is known as the self-consistency problem, okay, which is hard. But if you have a smart enough student like Udipan, he can actually do this. So what he did is he said, okay, I actually have to replace this radius dependence. I have to take into account that that radius at which a perturber is going around is time dependent. And you do the same calculation, and you get this horrendous looking expression. The only thing I want you to take home is that there's no more delta function, that's gone, but I have integrals here over the entire past time history of my system. In other words, what this is telling you is that the present day torque that I feel if I'm sinking in depends on the entire history of me sinking in through the system. Which makes sense because that sinking in perturbs the distribution function that in turn has an impact on the perturber. And this is known as the memory effect, or we call it the memory effect. And you can actually calculate and see what it does. Okay, so here's our previous situation. And now we compute the same thing using that horrendous looking expression, and we get this line. And you see that it follows Chandrasekhar. Then it gets close to the core, and suddenly it accelerates. And this is actually seen in numerical simulations. This is sometimes called super Chandrasekhar infall, just prior to stalling. Now, we can also do the other thing. We can put the perturber inside the core. Okay? And if you now use Chandrasekhar, Chandrasekhar says, well, it should just sink. The LBK torque itself says, well, the LBK torque is basically vanishingly small because the number of resonances becomes small and the resonances themselves become weak. So the LBK torque predicts this. If you compute this now with this more complicated looking memory term thing, you get this. It actually gets pushed out. So a very, very complicated treatment of dynamical friction includes core stalling and dynamical buoyancy. So we're done. We have an explanation. Except that there is this nagging problem, and it's the following. We have used perturbation theory to derive an expression for the torque that tells us that the torque comes from resonances. Now, where does perturbation theory fail? At resonances, because at the resonance I get a large response and nothing remains small. And this is a standard problem in this sort of field. Now, Tremaine-Weinberg were aware of this, and if you read their paper, they have a long discussion about slow versus fast regime, and they basically argue, well, this LBK torque thing only works in a fast regime because you want your perturber to sink quickly through the resonances so that I don't have time for my resonance to go nonlinear. Okay, that's true, but now you want this thing to go fast, and earlier you had assumed basically a secular approximation and an adiabatic limit. So there is this tension, there's this problem. And Udipal and I realized that what we need to do is we need to go and take this to a non-perturbative approach. And the way we're going to do this is we're going to just take a spherical system, put a perturber on it on a circular orbit, and then integrate orbits for the particles in that fully time-dependent perturbed potential. Now if I have a time-dependent perturbed potential, energy of the particles is no longer conserved, angular momentum is no longer conserved. When the particle changes its energy, it loses energy, that means the perturber gains that energy. And if I now sum over all possible orbits, I basically can work out how much energy my perturber gains or loses, and I can do dynamical friction. I'm not advocating this as a method to calculate dynamical friction, you might as well run a simulation, but this is how we're going to get some insight. Now to make a long story short, basically, we found that dynamical friction is mainly due to stars that are in near co-rotation resonance with the perturber. Okay, so they have a circular frequency that's about the same as that of the perturber. Not exactly the same, but about the same. And one of those is this horseshoe orbit I'm about to show you. Now first let me tell you what you're seeing here. This is the inertial frame. You're going to see this perturber going around, and this is one star particle that we're integrating in that time-dependent potential. Here you're going to see the energy of that particle as a function of time, and here you're going to see the same thing but in the co-rotating frame. Okay, so in the co-rotating frame the perturber stays here, and I have these Lagrange points that you're all familiar with. Okay, so let's start a simulation, calculation. So you see the perturber, the star is minding its own business, but because the star goes inside, it goes around a little bit faster than the perturber, which is further out, it catches up. And at some point it comes close to the perturber and it gets pulled out to a larger radius. Its energy undergoes a very large change. Okay? In the co-rotating frame, now it's outside, now it goes slower than the perturber, so the perturber is going to catch up. That basically means you get a slow drift here in the co-rotating frame. And at some point, when the perturber catches up and they get close again, guess what happens? This star gets pulled back in. It sort of moves in now to the inner arc here of this horseshoe. The energy comes down, okay, so the energy changes again, and we're done, and we've made a beautiful horseshoe orbit. Now, two things to notice. First of all, this energy change is the same as basically is directly linked here to the angular momentum change, and angular momentum change is torque. So when the particle gets pushed out here, the perturber basically reacts by going in. So at this point here, this particle contributes to dynamical friction on the perturber. But a little bit later, that same damn particle contributes dynamical buoyancy by making the perturber go out again as the particle goes in. And the net effect of this is zero because this energy goes back to its original value because the Jacobi energy of the particle is conserved. So how the hell am I going to get net dynamical friction out of this system? It just goes back and forth. Remember, you have that sine function, right? Each particle contributes both friction and buoyancy. Yes, it does. But how do I get a net effect out of this? Well, for that, we have to realize, first of all, that each horseshoe is not just one particle. There's a whole slew of particles that follow the same orbit, but just with different orbital phases. I can calculate the phase distribution along this orbit by using my unperturbed distribution function. It basically tells me how many stars are there at a given location with a given velocity. And this is sort of what is shown here. This sort of shows a density map of stars along this horseshoe at time t0. And now when I let this go, what happens is this overdensity is going to move behind the perturber. And when it's behind the perturber here, it's basically is this wake. And it's pulling on the perturber, and I get a dynamical friction. But of course, this overdensity now moves along, and at some point it's going to find itself here in front of the perturber. It's going to pull the perturber out, and the entire orbit is contributing dynamical buoyancy. So still my question stands, how the hell am I going to get a net effect out of this? And the answer is coherence. It turns out that all horseshoes do exactly the same. They start out by first contributing dynamical friction. And when all the horseshoes do that, it pulls the perturber in, and now the frequencies change because the perturber frequency has changed, so you basically never get to this stage where this contribution from dynamical buoyancy comes. And that's ultimately how you get friction out of this thing. Now, as I said, we found that most of the effect comes from 3 different kinds of near co-rotation resonance orbits. So we have the Pac-mans, I've shown you that one. Okay. There's another class of orbits that do almost the same. They're called tadpole orbits. They basically librate the L4 Lagrange point in the co-rotating frame. This one librates around L3. There's this sort of thing going around. It's called a libration. Right? Tadpoles are very well known in planetary dynamics. Right? Think of the Trojan moons of Jupiter. They're basically tadpole orbits. Horseshoe orbits are also very well known. But we also found a 3rd class of objects which we had never seen discussed in the literature. Turns out that you can only find those in a chord density distribution. And we decided to call them Pac-man orbits for an obvious reason. Right? It turns out that they're basically almost the same as a horseshoe, except the horseshoe orbit has to go around the center here, all the way around, because if there's a valley or a mountain here in potential space. Right? This orbit has just enough energy to make a shortcut and go over the hump here and go around. Okay? It's the only difference. But it turns out that these Pac-mans actually are very crucial for understanding core stalling. Here's the same picture, but now for a Pac-man orbit. Okay? And it turns out that all these Pac-mans do the same thing. They first contribute dynamical buoyancy when you get them going. Okay? So they first contribute dynamical buoyancy, they push. So if the Pac-mans would dominate, they would push the thing out, and you never get to the stage where they contribute dynamical friction. And now the key insight to understanding this all is the following plot. This is showing the effective potential, okay, coordinates of the effective potential in the orbital plane. So here's my perturber, here's the center, here are your Lagrange points, and I've color-coded it by the area. If you start your orbit integration here, say, then basically it contributes a tadpole orbit. Okay? So the tadpoles are color-coded in red, the horseshoes here are in blue, the Pac-mans are in green, and those are the 3 orbits that contribute to dynamical friction. Okay? This is the case for when I have a chord potential and a perturber outside of the core. I'm dominated by tadpoles and Pac-mans, no, by tadpoles and horseshoes, and they contribute friction. Okay? You also have orbits here in cyan that are called, we call them perturbophilic. They basically go around the perturber, and they do that very quickly, and because they're close to the perturber, they change a lot of energy with the perturber, but it goes very quickly, and the net effect is basically 0. They contribute 0 because it goes very quickly. What you need is a long libration time, and then go here in response to be able to get something out of it. Same thing for the centrophilic orbits here. They just zoom around the center. They don't do anything. Net effect 0. Okay. Now the crux here of the story is that once you do the same calculation, but now you put your perturber inside the core, you get this plot. Something dramatic has changed. What has basically happened is that this L1, L0, and L3 Lagrange points, they have merged. This is a bifurcation. A bifurcation has happened. I'm only left with L0. And this chokes off the horseshoes. The horseshoes are completely gone now, and I'm dominated by these Pac-man orbits. And it's these Pac-mans that do that pushing that cause dynamical buoyancy. Okay? For comparison, if I do the same thing in a Hörnquist sphere, okay, where you have a central cusp, whether you're outside the cusp or inside the cusp, nothing really changes. Note that there's no green here, there's no Pac-man orbits. Pac-mans only live in cores. Okay? So, I think, well, this is basically a complicated figure, just to show that this is bifurcation. I'll skip that, and I'll just put up the conclusions. I think the correct way to think about dynamical friction is really one in which a perturber pulls particles in and pushes them back across co-rotation, goes back and forth. And the only reason why you get a net effect out of that pushing back and forth across co-rotation is because of the gradient in the distribution function. Right? Remember that gradient in the distribution function that appeared in the LBK formula. It's the fact that you have slightly more stars that get pushed out than pulled in. Okay? If you're outside of a core, the horseshoes and tadpoles cause a net friction. Once you approach the core, suddenly a bifurcation in Lagrange points occurs, and that gives rise to Pac-mans, which cause a net buoyancy. Okay? So the upshot is, I think this core stalling and buoyancy are real dynamical effects. Initially, I thought that they might be numerical artifacts in simulations, but I think they're real. I think it's real dynamics. Okay? I think we actually even understand it. But the implications are kind of profound. Okay? We always talk about cores, and we want cores in all these galaxies, But if it really is a core, and this really operates, how the hell am I going to merge two black holes? Okay, you can't make a supermassive black hole in those things by merging. Shouldn't be able to. How do I get a nuclear star cluster? At least I can't form a nuclear star cluster by merging two globular clusters, for example, which is a favorite idea, how you make nuclear star clusters. Now, to what extent is this consistent or not with the idea that we see sometimes nuclear star clusters and AGN in dwarf galaxies? I leave that open for discussion. Thank you.
Thank you. Fascinating story. Let's start over there.
I have many questions. I'll just pick one. From the first part of your talk, it looks like the emergence of positive torques is really a question of how the perturber is introduced to the system. So we took two extremes, the immediate introduction and a very slow one, but in between, so the reality is somewhere in between.
Mm-hmm.
And it seems that the effect of the positive torque would be in reality weaker than the immediate introduction. So I think my question is how the strength of the buoyancy will look out in real, for example, in galaxy mergers, because it will not be very strong because it's not immediate introduction, but not very weak. So, yeah, in a real scenario of galaxy mergers, what will be the importance of buoyancy?
I can't answer that with a simple approach. Okay, this just gives you an idea about what the torque is at a given moment. And you're absolutely right, right? And then this is what I meant with you have to do this memory effect and take that into account. I mean, trying to do that, but even there, I'm not sure that that's, you know, linear perturbation theory is good enough. So basically, you need to look at the simulations, okay? And the simulations tell us there is this buoyancy effect, right? It doesn't want to go into the core. It comes there, and you see these oscillations. It goes in, and then it gets pushed out again. And it keeps going back and forth, basically, across its core. So I think the simulations show buoyancy. We're actually doing a number of experiments where we actually vary the details of the core, and not every core is equal. I mean, it seems to depend very strongly on how sharply you transition from not core to core. And if it's sharp enough, you get buoyancy. If you do it very gently, you go to a constant density core, we don't seem to see core stalling. So there's many open questions, and I share your concerns.
Okay, next question by Brent.
So you almost answered my question there. I was wondering whether there's some kind of critical inner slope for the presence of these Pac-man orbits, but you seem to suggest that maybe it has to do with the hole shape, which tells me maybe it's the distribution function shape rather than the density profile. So
yeah.
Is there some combination of energy and angular momentum that then changes the shape of the distribution function that gives you these orbits?
So you're nailing it. Basically, initially we thought, okay, it's all about this bifurcation, right? As soon as that bifurcation happens of these Lagrange points, then I get this transition, and that's it. Turns out what we're now finding is that that's not sufficient condition. I also need to have a distribution function, dFdE, that really becomes shallow. And if you go, for example, to a Dehnen sphere with a gamma of 0 that has a constant density core, but the dFdE actually turns up. And in that case, we don't get this effect. So you want also a very shallow gradient distribution function to go get together with this. Now the problem is, in your simulation, people have done simulations where they take an object and let it sink in a Dehnen sphere, and they see core stalling. But again, the problem is, once you do that in your simulation, you let the system go and it starts to sink towards the center, you now perturb your distribution function, and you may have actually turned your distribution function from cuspy to shallow. So it's a complicated total story, but yeah, you're basically absolutely right.
Okay, Nir.
Thanks. Very, very cool. Two quick questions. One, this may be related to what was asked before, but even in the instantaneous approximation, you showed that the horseshoe orbits are always initially going to contribute to the friction, and the Pac-man orbits are always initially going to contribute to the buoyancy, even though on average they both do both. I find that confusing because if in the instantaneous approximation, wouldn't it depend on when you introduce the system to what the particular phase distribution is at that instant? Yeah. Why do they always instantaneously do one or the other? And the second question is just related to your final discussion point about how do we merge stuff together in cores to get, for example, nuclear star clusters, et cetera. What about inertial effects? If the thing is initially flowing in on some high orbit, presumably this takes time to operate. Couldn't you just have enough velocity to reach the center before you get kicked out and merge that way?
Let me answer the second one, because, I mean, what we've done so far, because we're trying to do this analytically, is circular orbits, right? And you're right, maybe if I have an eccentric orbit, I will still go through the core. But whether I can, settle and ultimately get into the core, I think, I'm not aware of any simulation who has studied this with non-circular orbits. So that's one thing that needs to be done. Do you see core stalling also on eccentric orbits? Your confusion is absolutely right about the first question. I mean, it's everything changes, right? So in reality, once you let the system is coming in from above, and then you already have perturbed your distribution function. Whereas when we do the calculation, we are using the unperturbed distribution function to map the density of stars along these horseshoes and stuff. But in reality, I already have a perturbed distribution function. So in the second part, we did not try to account for this memory effect, which we've earlier argued is important. But there's only so much you can do before your brain hurts.
Maybe the next speaker can set up, and we'll take a final question from Daniel.
Very interesting. But in cosmological simulation, we see many perturbers. So, for example, if you have now an experiment with two massive perturbers, if you have a symmetric distribution, like both perturbers at both sides of the center, just because of the symmetry, you don't get any the same diffusion of orbits on both sides and no net effect?
I think it's a great question, and my gut feeling, but that's all it is, would be that indeed you may, because it has all to do with coherence, right? And if you have multiple perturbers going around, you may not have the perturbance needed to create a buoyancy, and maybe that's all you need then to still get mergers going. It's a very good idea.
Okay, thank you. Let's thank Frank again for a fascinating story.
So we want